Okay, I put out the test one out there in this week's folder. It's not due till next week, but um, it is timed. You get 3 hours to do it. Um, Obviously, it's open book, open note because you're at home and so forth. I also put a link out for this product called LogiSim, um, just to show you how to set it up and everything. You click this, and it'll download a file. It's a zip file. It's a compressed folders. Assuming it finishes, there it goes. You can right click on it there if you're in Google Chrome, choose Show in Folder. If you're not in Google Chrome, if you look in your Downloads folder, you'll find it. And then I'm gonna right click on this, and I'm gonna choose Extract All, and then click Extract. This is 1exe, so there's nothing to install. You can put it on a flash drive if you wanted to. It's a free package. It's like it was came up with by Hendrix College. And first thing I'm gonna do today is show how to use this. So we're on this page. So we got X and Y coming in. Now there's a text feature here. Edit text in the circuit. There's an add pin. And there's an add pin here. This add pin, if I click it on here, this is input. And I think if I click there and click over here, I can type. But that's I think that's X. Let's try this again. That's X. Now there's not a whole lot of frills to this package, but you can move things around a little bit. Oops, you can do that. There we go. I'm trying to think how to make this bigger so you can see it a little bit better. Might not have a zoom feature. No, I don't see any. Let's see, grab those. No. Okay, so then we'll create another one for Y. So those are going to be our two inputs that are going to come in. First thing we got here is what looks like multiplication. That's our AND. They got the most popular ones up here. You see there's a AND gate right here. And I click there and drop that in there. Now to connect these inputs into this AND gate, if you put your mouse over the far right here, you see it becomes a little green circle. If you click with your left mouse button, hold down and drag, you can then draw it over there. Now if you need to bend it, like right there, I can go straight. Now it would work, but if I wanted to bend it, I come here and then I move my mouse down and then let up on the left mouse button, click down again and drag over to here. Okay, then I do the same thing here. So I'll left mouse click there, come up, go over. Doesn't have to come up to work, just has to go from here to here. So you connect it however you want. Now if I have this come out, this is going to give us our output. And this is the other one. Sometimes I get this mixed up, which one's the output, which one's the input. But there it says X because nothing's coming into it. And I click and move that over, and we got 0, 0. Gives us 0. That's this right here. 0 and 0 is 0. 0 and 1 is 0. So if I come over and you click the little hand here, it looks like a little finger pointing. That's how you push it to the other one. So I switch that one on. So you can imagine voltage going through that piece right there. So 0 and 1 is 0. Click it again, and it shuts it off. And that's this one, 0 and 1, 0. 1 and 0 is 0. Okay, so if I click that, then you see we still get a 0. Because 1 and 0 is 0. Now if I click both of them, then you see that switched on. And that's our AND gate. Now you can move these around afterwards, kind of however you want. Instead of grabbing the middle, I grabbed it by this, and it created this extra line. How you get rid of those extra lines? You right click on them, choose delete. And I'll bring that one down. Now, if it asks you to, any assignment or so forth, asks you to create one of these diagrams, very easy way in Windows 10. A very easy way in Windows 10 is to just grab a screenshot of it. So you can do your Windows button, the one with little windows, the 4 little rectangles or whatever. You hold that down, you do Shift S for select, and it brings up this and grays your window out. Now if I click and hold down and drag and then let up, that'll copy that to the clipboard. At that point, you can paste it into a Word document, you can paste it into Paint or whatever. So I can go in 3D. And how do I paste? Do a Control V, but I don't. Just paste. And that brings that in. And there would be your logic diagram. Okay, that was the end. Let's look at the OR. It's this one here. And again, I need to have these coming into it. Notice it has extra connections here. That doesn't matter. I wonder. Although I don't think I ever designed anything that way. I wonder what would happen if you had more than 5 inputs. Show attributes. Oh, down here. Number of inputs. 12. Okay. I'm learning myself. Change that back to 5. Now these are similar to the design tools that somebody that's going into the field is working with, but there's a lot more robust in certain features, has a lot more simulations they can run, a lot more optimization. I don't think this one has any optimization from what I've seen. Well, maybe I lie. Analyze circuit. Compute in truth table instead of expression due to label. Minimize. Look at that. Oh, that's too cool. I didn't realize this was here. Build circuit. We had to look at one of those ones we had simplified, and what I did is I left mouse clicked somewhere in there and I dragged it up, so I highlighted everything. That's interesting. When we select those, there it goes. Delete. Okay. I'll look for something a little bit more interesting then. I didn't go through and build the truth table for that, but on page 48, we have that x plus x is equal to x. So gonna have my input coming in here is 1x. And remember that plus is your OR. And now if I want to branch off on that, I just clicked here in the middle on that green line I'm dragging down. So we're having x and x come in. And let's see what our output looks like. So this would be 0 coming through, no voltage or very low voltage. This would be 0 coming through here, again, no voltage or very low voltage. And that comes out as a single 0. Now, if I push that button, it comes out as that. Key part to note there is that whatever our input is matches our output. That's what they mean by x plus x is equal to x. Question is if I can Analyze circuit. Build circuit. We want to replace that. No, it doesn't optimize it. Because if it optimized it, you just have a line going straight through. Let's do a pretty nice job of that, though. I feel like I should be able to grab those white squares. But for life of me, I can't get hold of them. What other tool I have over here? That one in the hand. Hand just pushes on and off. Excuse me. See the simulation tree popping up. But here's our inputs coming in. 0 gives you 0, 1 gives you 1. So you can see that. And this is where you can put it in directly here in the build circuit for you. Let's delete this. A plus B times C plus D plus A times B. Equals X. Oh well. Obviously, I don't know how to use this tool right here. I'll stick with just doing it manually. Now, if we had something a little bit more complex, like on page 52, we have X, Y, and Z, so we have 3 inputs. If I have that select, I bet this will let me edit it inside. Yep, they're paired together now. Okay. So that's our X, Y, Z. And what we're trying to simulate this one right here. So it looks like we've got X, not X, not Y, don't have a not Z. So besides X is coming in, I also need to have, and I'll come back to that, but I'll come down here. And I need to have a not X. This is our inverter right here. This is what flips it to the opposite. And Y, same thing. There we go. So then we got 3 of these. And it looks like multiplication, so that's our AND. So 3 ANDs on there. And from that, looks like we're going to have 2 pluses, so 2 OR gates. What am I doing? Not 2 OR gates, just 1. Because all 3 of these are coming into that one. Okay. So we need X prime, Y prime, Z. Excuse me. I'm not very good at these. Excuse me again. So I think you get the idea. So that's X prime, Y prime, and we need a Z coming in. The idea on design is you can actually tell the difference between the lines. So when your input's coming in here, you should be able to easily tell them apart. Sometimes I get it so convoluted that it's difficult. Let's see if I can edit the label in that. X prime, Y prime, Z. X prime, Y prime, Z. X prime, Y prime, Z. There we go. This next one is X prime, Y, Z. Here's X prime. YZ. Let's come up there, so I'll have a branch off here. And that's X prime YZ. This last one is XY prime. So XY prime. And this one's Y prime here, so XY prime. XY prime. Now, the 3 of those are going to come into my OR gate here. for these pluses between them. And could label that. That'd be kind of wordy. Let's go ahead and do that. X prime y prime z plus x prime y z plus x y prime. That's almost useless. Why can't I grab these? Why would you design this where you can't resize that, though? Probably. Yeah, maybe it would distort what you really think of it. I don't know. I don't know if I can get back to that text or not. Yeah, there. Get rid of it. There we go. So now we need to have our final output. Going in like that. And they say that's equivalent to this right here after you reduce it to x prime z plus x y prime. Now let me come down here. And it looks like we have two AND gates and an OR gate. So two AND gates. An OR gate. So for our first AND gate, we're having not x and z. So I need to invert x and bring z up. Guess I can label these. X, Y, Z. Not X and Z. So I invert X. And then bring Z up. And our second one is X, not Y. Not Y. Okay, so both of these then are coming in. Let them have my output. Okay, their claim is, assuming I designed these diagrams correctly, is that these are the same. This is a simplified version down here. Well, let me see. 0, 0, 0 up here is giving me 0. And I'd have to go through all my possibilities to verify that. 0, 0, 0, 0, 0, 1 gives me 1. And sure enough, gives you 1 down here. In case you're wondering what I'm talking about. These are the test cases. These are all of our possibilities for X, Y, and Z. I already did the first 2, so I'm now down to 0, 1, 0. I think I did the first 2. Yeah, 1, 1. So that checks. 0, 1, 0. So this would be a 1. This would be a 1. Both of them give us 0, so that's equal. 0, 1, 1. So turn on this one, turn on this one, turn on this one, turn on this one. And that checks. 1, 0, 0. Turn that one, turn that one. They both give us 1. 1, 0, 1. They both give us 1. One, 1, 0. Okay, so that both give us 0. And 1, 1, 1. So all these are turned on, has the full voltage going through. It gives us 0, 0. Some of those simplification, have you done any of those simplification yet, Kyle? They some of them are kind of tedious, and you wonder if you got the correct answer when you're done. If you build the logic circuit here with your pre simplification and then your post simplification, if you go through all the possibilities, that'll tell you if it's right or not. Now it's possible it could be simplified down further, but it'll definitely tell you if the simplification you came up with is the same one as the original. Because if you go through all the possibilities, all of those, there is no other choice. Now, one thing I want to also point out on this, of course, now to turn that in, we can do the Windows Shift S and then select it. There's also an export image here, where you can export it as different formats: JPEG, PNG. Assuming that's how big it is. And then it'll ask you to save it somewhere. Okay, we do a new. That's nice. Okay, it's still up. I was going to say, most well-written software packages prompt you to say, do you really want a new? Don't you want to save your work? But soon if I close that, yeah, save it. I'll discard that. Now over here down this little box. Actually, I don't even know what that plus is there. But down this little box is some other items. Here's wiring. So if these were items you were designing an electronic device with, you can use them. Same idea. You drop it over here. There's a clock. Bit extender. Gates. There's a NOT gate we looked at. There's a buffer. What do you think a buffer does? Right. Yeah. So whatever comes in just goes kind of straight out, but like you say, it may be delayed slightly while it gets so much of it in there. And this was our NOT, and you see that the symbol looks exactly the same except there's a little circle on the front. Circle on the front is what inverts it to the opposite. So 1 becomes 0, 0 becomes 1. We looked at AND gate, OR gate. Here's a NAND gate. What do you think NAND gate does? NAND. Yeah. Yeah. So if I had two inputs coming in here, again, remember this AND is like multiplication. 0 times 0 is 0, but C gives us 1. If I flip one of those, 1 times 0 is 0, so it should be giving us a 0, but the little circle under inverts it, becomes a 1. But now if I invert that, 1 NAND 1 is equal to 0. So that's kind of nice when you're trying to wrap your mind around some of these concepts, which we're going to see a lot of these as the semester goes on. You can create a little diagram and see what it looks like. There's a NOR gate, which just inverts an OR. There's an XOR gate, which is something we'll look at here later. XNOR. I've never used even parity and odd parity in here, so I'm curious how you could do that. Also down here, there's plexers, multiplexer. Demultiplexer, decoder, priority encoder, bit selector. Here's an adder. Now I'm trying to think. Was it you that asked what's really happening inside of some of these sort of circuits? Oh, did you? But this is all we see from our design standpoint is this right here. We'll talk about flip-flops. Here's a register. RAM. So you can see there's a lot of different things you can program with this, or not program, you can design with it. Joystick, keyboard. We won't go into that much. Base. Writing tool, text tool, menu tool. Never ever used that. Okay, enough of the Logisim. So again, that's how you design anything in this this class with this package. Logisim. Download. Okay, from what I can see, it should run. If you got a Mac, it should run on it. It says any platform supporting Java version 5 or later. Don't know if anybody's using Mac, but if you are, then they should run on that too. According to their directions, I guess. I didn't look to see where we left off last time. So busy making sure that I knew how to use that tool still. Haven't used it for a year, so I'm digging into it and playing with it. Okay, so about sample 2.2. Yeah, I remember that. So we're on page 55. And example 2.3 says to find the complement functions F1 and F2 of example 2.2 by taking their duals and implement each literal. Complement, okay. So we have F1 equals X prime, Y, Z prime. plus x prime, y prime, z. Now, we were talking last time about how use De Morgan's theorem. Yeah, that was example 2.2 on the bottom page 54. But it says a simpler procedure for deriving a complement of a function is to take the dual and complement each literal. So we're trying to find a complement of this. Now realize these are binary inputs coming in. 0, 1, true or false, or 1 or 0, true or false, so forth. And so the dual, it tells us, is we take the addition here and we're going to rewrite it with multiplication in between them. And then we got x prime, y, z prime, and we rewrite those with pluses between them. So we got x prime plus y plus z prime. And then x prime plus y prime plus z. So notice that these had multiplication or ands between them. And so we rewrote those with pluses or ors between them. So not x or y or not z. This plus right here in the middle, that became our multiplication. Then it says, take their dual, which was what we just did, and then complement each literal. So the not x becomes x, the y becomes not y, the not z becomes z, not x becomes x, not y becomes y, and z becomes not z. And that would be our complement. If you remember right, that simplifying the other one was kind of tedious. I think there's one part on example 2.2 where I wasn't sure where it even came from. I think they had made a mistake. So this is a simpler way. Now, the other example I have is F2 is equal to this right here. Now, you notice that the first x, it wants us to do the dual. The first x is just alone. So we have this times this. Now, since our first x doesn't have any kind of operation in it, it just carries straight down. And since this is multiplication or and, this will become a plus or an or. And then inside here, these multiplication or ands become ors or addition. So we got y prime plus z prime. This plus here becomes multiplication or and. Then we've got y plus z. Because what looks like that multiplication there becomes addition or. Then it tells us to complement each literal. So that becomes not x. This becomes y. This becomes z. That becomes not y. Complement of y. This becomes not z. And that'll be our answer. Questions on that? Where could you use this at if you weren't programming a circuit? Well, if you had this right here, and X represented something like sales is greater than 100. Y represented that you had costs less or equal to 50. And Z represented by revenue is equal to 300. Well, this programming wise would look something like this. Sales greater than 100. Now this is our X, so we have our the not in front of it. So depending upon your programming language, it may look like that. And then there's an and. Not that I can do them, but there's ampersand above your 7. And then Y, which is costs, is less than or equal to 50. Then another and. And Z is revenue is equal to 300. And then exclamation in front of it, and then closing. And then you'd have an or, 2 pipe symbols. And then you'd have something similar here. If you wanted to take the complement of it, then what you could do is use the what we use this piece right here. So if you chose that piece, then that takes the complement of it. Does that make sense? Sort of. Okay. Let's see if I can actually do that then. I think I can do it in NetBeans. I know for an average person going just programming, it's just like, when am I going to use this type of deal? And probably never, but it helps you to really think through the Boolean side of it. The reason I said I think I can do it in NetBeans is because you have to have a Boolean data type to make it easy. Boolean X, Y, and Z. Didn't give me a little red squiggly, so it must have Boolean. And we said, just to make up something, so we got sales, costs, and revenue. So costs, revenue. Sales equal 300, costs is equal to 500, revenue is equal to revenue is equal to 30. X is going to equal to, I don't know if I need parentheses around this. I think I can do this. Because this will return true or false, and that's what this is Boolean. And Y is going to equal to costs less than or equal to 50. And Z is going to equal to revenue is equal to 300. Or 30. 300. Well, that's something questionable. That looks odd. Didn't squawk at it. And so, my result see if I remember how to do the not in Java. Result is going to equal to, and then I'll put in this first part right here. Not X and Y and not Z. Not. Oh, exclamation. What am I doing? Exclamation. I bet that's it. Yep, that's it. Okay, so not X and Y and not Z. Then there's a or between them, or yeah, an or between them. And second set of parentheses, we have not X, not Y, and Z. Not X, not Y, and Z. Gives us false. Okay, so result again. Now this is giving us the complement of it. The simplified version right here. So it should give us true. So we got X or not Y or Z and X, Y, not Z. So X, is that an and in there? I'm messing this up. These are ors. Okay. And ors. Those are ors. So X or Y or not Z. System out, print line, result. And it sees prints false and then true, which is what it should do, because it's a complement of that. So now I could equally have just put these conditions right here in for the X, Y, and Z down here. Now compare that to this. Gives you that result. In programming, all we do is we don't think that hard. We just simply flip that. So if your program's working opposite the way it is, it's real easy. Just put an exclamation in front of it. Now it should flip it to that. So if I run it again, see how it goes from false to true. Which one was easier, programming-wise? This method, right? Just put an exclamation in front of it to take the complement. That's not necessarily the best efficiency-wise, though. Oh, we're on a code? Let that absorb for a minute. Now that just is one possibility. You know, I put 3 conditions in here. I could equally just put a true, true, false here, or false, 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 which would be 0, 0, 0. So you could use programming to build a truth table. If you put arrays in there and went from 0 to 1 on X, Y, and Z, and then loop through them and so forth, you could print out results of this. I noticed that there was a project get circuit statistics here. Don't know how to really interpret what I'm seeing there. But this could be such that what we're talking about is designing efficiently. That's kind of the main goal of this chapter is how can you simplify it? How can you rewrite in different terms? How can you design it cheaply? So those are all things you need to think about. You remember that? I think it was in your programming class where I had you like do subtraction without subtracting. I think that was one of them. Was that the one? Okay. The idea on that is that some of these units you could put in here, adder, subtractor, multiplier, divider, and so forth. Some of these are expensive, and when you take that expense and you multiply it times maybe 10,000 circuits in a more complex device, and all of a sudden it becomes quite expensive. Okay, let me go back. Now, number practice exercise 2.4 is interesting. Because I want to show you going backwards. So I don't think we've looked at that. We looked at ones like this. You know, you have your X coming in. And by the way, this is a nice design they have. If it becomes more complex, which is what I probably should have done in some of mine, You put X, Y, and Z on top, and you have the inverter right next to it. And then he's come down here as straight lines, and then you have a branch off into the individual elements. Did I miss that? Have we covered that? I guess I won't flip back on the ebook. Let me flip back in my book. I don't think we covered that symbol yet, but maybe I missed it. Well, they introduced some of this back at the last part of chapter 1. Well, that's kind of bad. They haven't talked about that yet. Usually, that's a general rule. You don't put stuff in there they haven't covered yet. But that's good. We got Logisim. And this is our XOR gate. And let's skip ahead. Our XOR gate, let me write down the symbol for it. It's on page 68 where they introduced it. The XOR, symbol-wise, looking right at it. There it is. And you can see the truth table there to see what happens. With an XOR 0, 0 XOR 0 is 0, 0 XOR 1 is 1, 1 XOR 0 is 1, 1 XOR 1 is equal to 0. What happens there is if they're different, then it gives you a 1. If they're the same, it gives you 0. You don't need to know that for writing down that that design, but okay, so going back to that problem, sometimes it's easier to start here from the very end and work your way backwards. So this is an XOR. Means right here in the middle, going to have that symbol. Now they will show you here in the answer where they translate that. But then going backwards, this is X, Y prime. Now, if that X, Y prime wasn't here, this is an AND. You go back here, this branches back to X. This one branches to here, and if I go up, goes through this inverter, so that's a Y prime. So that's what would tell me the X, Y prime. This is coming down here, and this tells us it's not x, y. But again, if it didn't tell us that, I'd go through, follow these lines. That's coming back here, going back through the inverter, so that's my not x. This one is going to the y, which is up there. Now, what they came up with is not the item from here, but they took a simplified version of it. But since we haven't even really covered XOR, then that makes it kind of difficult. The XOR, assuming you had and it's not the equivalent to this. Let me use P's and Q's. Maybe that would make more sense. P and Q. This is coming out as a F. Tells us that F would equal to P not Q plus not P Q. So then, and there's lots of variations of writing this, but then you'd have to flip these because this is equivalent to this, which means this would be your P and this would be your Q. So then you'd have to come up with your not P and not Q, P prime and Q prime. And then you can plug it in here, do some simplification and so forth. Like I say, that was kind of a bad example they had because they hadn't talked about that. Okay, 2.6. Canonical and standard forms, min terms and max terms. As a binary variable may appear either in normal form, x, or as complement form, not x, x prime. Now consider two binary variables, x and y, combined with an and operation. Since each variable may appear in either form, there are four possible combinations. Got not x and not y, not x and y, x and not y, and x and y. Each of these four and terms is called a min term or a standard product. In a similar manner, n variables can be combined to form 2 to the n min terms. The 2 to the n different min terms may be determined by a method similar to one shown in figure or table 2.3 for 3 variables. Let's see. Each min term is obtained from an and term of the n variables, with each variable being primed if the corresponding bit of the binary number is 0 and unprimed if it's 1. Okay, so if these are, we got 3 binary variables, and we got our term here, not x, not y, not z. And that gives us little m sub 0. Notice this becomes, in terms of max terms, x or y or z. That's our uppercase designation. Oh, and I should point out, it's the prime. The prime is the naught, is the zeros. So you could come up with these fairly easy, and remembering that these flip over to here, your multiplication, your and becomes addition or, and then these flip to the opposite. Not that I'm going to finish this. But if we add x, y, z, and w. Zero, 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 zero. What would our midterm be? Or not the midterm, sorry. Because before the midterm, they have the actual term itself. I'm getting that mixed up. Okay, the term for the midterm. What would this be? Not x, not y, not z, and not w. Because these are all zeros. And then our max term. It seems so weird to say max term. These all flip, so they go to the opposite of wherever they were, and then instead of there being an and between them or multiplication, there's going to be an or between them or addition. So x plus y plus z plus w. So again, it's all based upon 1 being just the normal variable, 0 becoming the naught or the prime of that, and then this is these just all flipped and changing operation in between. So if I had this, that would be x, not y, z, and w. For the max term, that'd be not x, or y, or not z, or not w. Does that make sense on how to build those min terms and max terms? Okay. That's just what we're talking about here. A variable being primed with the corresponding binary number is 0. So if it's 0, you just prime it. Similar fashion, the n variables forming an or term, with each term being primed or unprimed, provide 2 to the n possible combination called max terms or standard sums. So you could start out over here, what they're saying. And then 8 max terms for 3 variables together as symbolic designations are listed in table 2.3. Okay. So you're just going back the other way. Blah, 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 blah. Okay. Each max term is a complement of its corresponding min term and vice versa. A Boolean function can be expressed algebraically from the given truth table by forming a minterm for each combination of variables that produces a 1 in the function, and then taking the OR of all those terms. For example, a function f1 in this table determined by expressing the combinations of 0, 0, 1, 1, 0, 0, and 1, 1, 1 as these respectively. Okay, so I think that's just from up here. Is formed from a truth table by forming a minterm for each combination of variables that produces a 1 in the function, and then taking the OR of all those terms. X prime, Y prime, Z. That I'm not seeing for some reason. See, I look at 1, 1, 1, which is x, y, z. Now that's x and y and z. So I can see where that give you 1, which is this down here. And I can see where that function comes from, because there's an or between those. Because 1 plus 1 plus 1 gives us a 1 there, right, doesn't it? But some of these other ones, like this, x, y, z prime. X and y, 1 times 1 is 1 times 0 is 0. Okay, I'm seeing it now. Does that make sense what they're talking about there? Okay. My eyes are just crossing. But yeah, since these right here, like for example, 1 and 1 and 1 gives you 1, and then they over here with the combine them together with the ors. Now, having come up with all those, then what they do is they create a new function out of taking the 3 of those and putting ors between them. So that's your M1 plus little m1 plus little m4 plus little m7. At F2, this is F2. Looks like all the ones it gives is zeros. Say F2 there, which would be our other ones we have. Important, a Boolean function will be expressed as sum of min terms with sum, meaning the oring of the terms. Consider complement of a Boolean function may be read from the truth table by forming a min term for each combination that produces 0 in a function and then oring those terms. See, they're taking this F2 here, that right there, and where are they taking this one? I'm not sure where they're getting that at. Forming a min term for each combination that produces 0 in the function. Oh, that didn't go up. These 5 here form zeros. And this is where they're then ORing those. So x prime, y prime, z prime is the first one here that has a 0. So x prime, y prime, z prime. This one is x prime, y, z prime. Okay, x prime, y, z prime. So then if we take complement of f1, f prime sub 1. Okay, so then those flip to the opposite. X prime becomes x, y prime becomes y, z prime becomes z. X prime here becomes x, y becomes y prime, z prime becomes z, and so on. And the addition that's between each one of these here now becomes multiplication. Now, if I look these up, x plus y plus z, x plus y plus z is capital M sub 0. So that's why down here they put a big M sub 0. They look these up. Similarly, it's possible to read the expression for F2 from the table. Suppose by looking over at the ones and zeros over there. These examples demonstrate a second property of Boolean algebra. Any Boolean function can be expressed as a product of max terms with product meaning the ANDing of terms. Procedure for obtaining the product of max terms directly from truth tables as follows. Form a max term for each combination of variables that produces 0 in a function, and then form the AND of all those max terms. Boolean functions expressed as a sum of min terms or product max terms are said to be a canonical form. And I think I'm going to stop there because that's a good stopping place. So we'll start with the sum of min terms next time.